In Module 8, we're going to be talking about decision trees. By the end of this module, you should be able to explain how a decision tree or a classification and regression tree model or CART model functions as a classifier or a regressor, explain the general process used to grow a tree, understand and explain the concepts of entropy and the Gini impurity index and compare and contrast these measures, and then take the knowledge that you have learned and use it to implement programs in Python and scikit-learn for these different methods. So when we talk about growing a tree, basically what we're talking about is the model fitting process. So I've got some code on the screen here, and this will be put up on the website as well so you can step through it. But the process here is to take the data points, in this case the set of colors on the right hand side of the screen, and train a model so that when new colors are found, they are fit into the appropriate categories. So I've got a nice representation of data here from reds and greens and blues that in theory are from the sample distribution of our overall population of colors that we want to learn to predict from. Now this is very much a toy model, so don't read too much into the complexity of this as we're talking about it. So if we look at the code, what's happening here is we have this thing called a split threshold set at the top, and in this particular case it's 2.0. Now, this is very important, as we'll see later on, especially when we start to get to similar training instances, because this determines whether or not it's worth creating a new node in the tree, and we'll talk to that in a bit. So I've created two Python classes. The first one is a node, and this Python class basically has a pointer to the left of the node, a pointer to the right of the node, and the value of the current node. And in this type of decision tree, what we try to determine is at every level we determine, is the current node within a certain range of the value that we're inspecting, or is it less than the current node, which means we would traverse to the left hand side of the tree, or is it on the right hand side, which means we would traverse to the right hand side of the tree. So the next step here is just a simple function where I've implemented the repr method, and that gives us a quick and easy way to print out the contents of a node, and we'll use that when we start debugging the code. I've also implemented a tree class in Python, and the purpose of this tree class is to build the tree as part of the fitting process. So the tree class simply has one property, and that is the head node of the tree. And as we go through this recursive fit tree process, we will add more and more nodes into the tree for different levels of decision. So the next thing is this fit tree process, which takes in a parameter of a data set that we want to fit a tree to or train the model on. And it takes in two optional parameters that have default values. The first one is this depth of 0, and the second one is a value for the head node. So when we first come into this algorithm to train, all we pass in is this data set D. We don't pass in any depth or any head values for these parameters because these are used for the recursion of this thing, and we'll see that as we walk through it. So as we come into this fit tree method here, the first thing we have to do is check to see if I've passed in a head node or not. If I haven't passed in a head node, that means that I'm on the initial iteration of this algorithm. And by being on the initial iteration of this algorithm, basically what happens is I get the first value and I get the first value using a very simple method. I have a range of colors here from a bright red to a bright blue and a bright green, which is somewhere in the middle. So if you think about an RGB color, this is a collection of red, green, and blue values, usually in hex. So if I'm looking at all red on this end of the spectrum, I might be looking at something like FF0000, which means all red, no green, no blue. Somewhere over here in the middle, I might have something that's more or less all green, no red, and no blue. And then something here over on this side, I might have 0000 FF. And this corresponds basically to the red, the green, and the blue components of the colors. So as I'm going through and identifying a color that I want to pick out, what I want to pick out is the mean value of this population. So if I flatten this thing out and don't look at it in the 3 dimensions of RGB, but if I flatten this thing out and try to find the mean value from one side to the other, what I might end up with is something that looks like this gray color here. And this gray color, just for the sake of throwing a number out there, let's say that its RGB pattern is 7F, 7F, 7F. Now, an important thing to also know so that you can get an intuition for this, if I have the same proportion of red to green to blue, I basically end up with a continuum from black, which is 000000, to white, which is FF, 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 FF. So all the guns on wide open, it's white. All the guns turn completely off, it's black. And every other shade of grade in between is every possible value for each of these, as long as they are exactly in the same proportion or almost exactly in the same proportion to each other. So when I say median, or the mean value between these, what I'm really talking about is the mean distribution, or the mean proportion of red to green to blue. So the mean there is going to be a shade of gray, and that's what I'm going to pick to be the head node in this case. So the head node is none. I create a new empty node element, and for the sake of my code, I set the current value of head equal to that head node that I just created. Then I go through and I try to figure out what is the index of the value of the element in the array that is closest to the mean value here. So in this case, if I take from 1 to 24 and divide this thing up, what I'm really looking at, and when I say 1 to 24, I'm talking about these input values down here. If I'm looking at 1 to 24 in here, what I'm really looking at is something less than 12 as probably being the mean value. So what I end up with is something in there. So I go in and I use this np-argmin capability to find something that is the closest to the mean value in this array D, and I capture the index position of it. And we'll look at this when we go into debugging in just a bit. And then I assign the value of the head node equal to that value in the index. If there are still values to the left of this mean value. I take a slice of the D that was passed in from 0, which is the first element, up to IDX, which is the value that we just assigned to the head node. And if that length of that set is greater than 0, we call fit tree recursively. And we call fit tree with that subset of data that represents everything to the left of the head node that we've defined. And we're going to the next level in the tree. So currently I'm sitting here at level 0 in the tree. My next level down in the tree is going to be level 1. So, and I pass in the head node. And at that point in time, this all recurses back up to here. So by recursing up to here, I've now called it with my new head node. I've called it with everything basically to the left side of 9. And that gives me an array D of 1, 2, 3, 5, 7. So now I'm going to skip down to this else section because head has a value. I passed it in. And once again, just as a safety check, I make sure that I passed in an array that has more than 0 elements in it. And I do my check again to see if the absolute value, actually this is a new check. I check to see if the absolute value of D sub IDX, which is this mean value that we just pulled out, minus the value of the head node is less than some split threshold. If this case is true, what we have determined is that this boundary around the last node has not been sufficiently breached in order to make it worth creating a new node in the tree. So let's say that I presented with my next training element that was only either slightly lighter or slightly darker than this head node. In that case, if the threshold has not been exceeded, I simply assign it whatever label was given to the head node, and then I recurse again. If I have exceeded this split threshold, which if I passed in these red, brown, and green colors, because that would be significantly different in color than gray, at that point, I want to go in again and figure out which one of these is the next node to implement. And I want to check to see if the value of that mean node is less than the current head node, or if it's not. If it's less than the current head node, I create a new node to the left and I assign the value equal to the current mean node that we've identified. And then we recurse again with the remainder of those values. We'd call fit tree again. If we had gone to the right, if the new value had been greater than that, we would have called fit tree with the values to the right. So what does this look like? So once again, over here in our tree, the next mean element is brown. So we create a new node to the left. We assign the value of brown to it. And then, since we created it to the left, we recurse left again with the remaining values of D. And surprise, there's only one value in there, and that's red. So now we create our next child node to the left. So in this data set, there's no more training elements to the left of red. So this returns, and it's going to return up to this level, because this is where we process the brown node. So head.left at this level of the stack recursion has now been set, and now we call the fit tree to the right. And when we call fit tree to the right, what we end up with is this next value being selected. And it goes fit tree to the right because this teal color is part way between green and blue, but it's also greater than this gray color here. So we continue to do this. We've called that. We recurse again to the left. Green is going to be to the left of teal, but to the right of gray. So it gets moved over here. And then same thing with blue. Now we've got a full decision tree here that we've built at this point. So what happens when we get this color that's only slightly different than gray? It's a slightly different shade of gray than the one that our head node is at. So at this point, we do our check right here to see, is the new value minus the head value less than the split threshold? And in this case, it is. They're slightly different shades of gray. So in that case, we basically just assign this the same label that we assigned the head label. So what's the danger with a very simple decision tree like this? Well, what we've done here is we've created a tree, and that tree has effectively learned the data. So if we come over here to the actual code, and I'm going to run this code and then do some tests on it. Let's take a look at what we have. So as you remember, down here at the bottom, we've ran this with values of NP array 1, 2, 3, 5, 7, 9, 12, 16, and 24. We create a new tree called T, and then we fit that tree to those values. So up here at the top, I currently have a split threshold of 1. So when we run this and we examine what we have, we see that the head node in the tree is the value 9, and the value immediately to the left is 3, and the value immediately to the right is 16. So 9 is the median value here as determined by our cost function. And at the next level, the median value between 1 and 7 is 3. And then on the 9 side over here, the median value between 12 and 24 is 16. So if we continue to inspect our array nodes or our list nodes, we see that this continues to play out, and so that builds our entire left-hand side of the tree, and our right-hand side of the tree is fairly shallow since its next level is 12, and then I've got the left node, our next level is 16, our left node is 12, and our right node is 24. And at that point, I've consumed the entire data set. So back to our problem at hand, we've effectively overlearned this data set. So what we mean by that is the learned tree is the training data. So we've effectively overfit the model, and we can assume that even though our precision is awesome in this case, our recall is probably going to be poor because we have fit the training data and it doesn't take into account any variance at all in our system. So we affect this by changing the split threshold that's up here to some value that is enough. Perhaps we might set it to the standard deviation of our data set. And that would give us a better grouping, potentially give us a better grouping of items in our data set. I don't know. It's something you're going to have to work out. And the reason you have to work it out on an example by example basis is this is a greedy method. And we'll get into what greedy method means in just a bit. But because it is a greedy method, it is not necessarily making the optimal decision. It's making the most productive decision it can at each step. So these problems are overcome in more advanced methods such as boosting, bagging, and random forest because we realize that just regular decision trees aren't really all that useful in most real-world cases. So when we're putting together a tree, we use a cost function to determine if a new training example is sufficiently different than the prior known nodes to warrant a split in the tree. Now, why do we care about determining whether it's worth splitting the tree or not? There's two reasons. One is splitting a tree can be a very costly operation on a very large data set or a very large training data set. So the more frequently we split the tree, the longer it takes to train. It also takes more memory and time. So we want to split the tree as much as is necessary to produce a good model, but no more than absolutely necessary to produce a good enough model. So there's a couple of different ways that we implement cost functions in our process. One is if we're learning a regression model. So this is a classification and regression tree model. So it can do both traditional regression as well as classification. So in the case of a regression tree, given an input, we're trying to learn an appropriate output or learn the correct output given that input. So in this case, we're simply looking at something like mean squared error being the measure of fit in that case. Whereas if we're talking about classification models, there's a couple of different ways to determine the cost. The first off is the cost of misclassification. This goes back to your precision versus recall trade-off. So you need to make sure that if you are erring on the side of a more simple model, that it's okay to have a certain amount of misclassification. 100% models are seldom, first off, worth building, and secondly, 100% models typically have poor recall. Another method that we use and we borrow from information theory is the concept of entropy. And entropy in this case is how much new information is gained or created or identified by creating a new class or a new split in the model. And we're going to talk about this in depth in the next slide. And the other one is the Gini index, which is similar to entropy, but basically instead of trying to figure out whether it produces new information, is that it produces purity in each of the nodes that are created as part of the process. So entropy is the measure of information in a message. So how much new information is contained in the message? And something to understand here is when we're talking about a message, what happens if the exemplars are evenly distributed across all of the classes for a given test? So if it's evenly distributed across the classes, the entropy is approximately 1, meaning that the split adds no increase in information. So in that case, doing that comparison would yield no knowledge whatsoever. That would be the epitome of the worst possible split ever. So there's two things I want you to look at here. One is down here where we're calculating the entropy, and we're calculating the entropy per this equation up here. And there's a couple of components of this equation. So the first component of this equation is the probability of a particular contribution occurring or not. So this is simply the number of members of this class divided by the number of total members in the sample. So in our example down here, if we have 54 members in our sample and we have 27 in class 1 and 27 in class 2, those are equal. So if we sum these two classes up and multiply the probability of each class times the log of n, which in this case, since there's two classes, would be 2 of the probabilities, what we end up with in this case, which means that this is a poor choice for a decision criteria. So we would be better served by trying to identify a different value. So what happens if there's 3 classes? In 3 classes, we do something very similar. I still have 54 values in my total sample size, but they're split evenly across 3 different classes. So there's 18 in each one for this determination. So I change my logarithm to use a log base 3 in this case, since there are 3 classes. And I add these up, and lo and behold, I get an entropy of 1 again, indicating that it's a poor decision criteria. So if we're talking about pure CART models, they always use binary decisions. So in a pure CART model, we would always use log 2 in this determination. So let's move on to the Gini impurity index. Here this is referred to as the Gini index, the Gini impurity index, Gini impurity, number of different things. It's all the same thing. And basically what we're seeking to do at each split is to fit as many pure classes at each level of decision as possible. So what that might mean is, and we'll go back to our iris data set here, our first fit would be to try to take that completely linearly separable class out and split it into its own decision node. So in our example here, we start off with the decision that if petal length in centimeters is less than 2.45, less than or equal to 2.45, what this does is it creates a split of all the exemplars. And it creates a split of all the exemplars in such a way that everything in the iris setosa family gets put into one node as a result of that decision. So this is a completely pure node. And this node over here is a split node. So in terms of impurity at this level, at the top level, I've got 150 samples. I've got 50 in each of the 3 classes. So when I compute this formula up here for the Gini impurity index, once again, I'm using the probability of any one of these samples being in a class squared, and I'm summing these up over the number of classes in and subtracting it from 1. So when I do the math over here for the top level node, I get 1 minus the quantity 50 divided by 150 squared minus the quantity 50 divided by 150 squared minus the quantity 50 divided by 150 squared. And I end up with this Gini impurity number of 2/3. What this tells me is that 1/3 of the data can be separable. The other 2/3 of the data is not separable by a single decision. So when I split that out and then evaluate it at the next node, the Gini impurity of my left-hand node is perfect. It's 0.0 because for 50 samples, I have all 50 values in a single class. So this would be what? It would be 1 minus 50 over 50 squared, which is 1. So 1 minus 1 gives me a Gini impurity of 0. So in my remaining class over here for petal width less than or equal to 1.75, what I end up with is a split. I end up with a split of 100 samples, 50 in each class at this node. So 1 minus 50 over 100 squared minus 50 over 100 squared is 1/2 or 50%. So that matches my Gini impurity for this node. Now, when I split and go to the next node, I'm hopeful that this Gini impurity will continue to go down at each future decision point. So this is the Gini impurity that we use for decision trees. So the next thing that we want to talk about are cart trees, because cart trees are a fairly commonly used decision tree algorithm. This is the decision tree algorithm that is implemented in scikit-learn, and it uses a similar recursive partitioning operation to the toy example that we looked at the beginning. So what we try to do here is at each level minimize the improper classification as we train the tree, just like we did in our toy example. And CART always uses binary trees. CART will never use an n-way tree for decisions. So that simplifies things significantly when you're running on lower powered computers. So in this example, we've got a tree that we've already learned. So I've got an element up here that's sort of a pinky gray, and that's kind of my mid-level node. So in this case, my node is either significantly different than the next decision or not. So if I'm at this node and I get a color in that is this bright red color that we're testing for, I need to determine, is this more like the conditional value that splits to the left, or does it need to go to the right for the next level of decision? So in this case, this bright red is closer to this orangish color than it is to this bluish color. So as I move to the next level of the tree, I need to determine, is this red color similar to the node I'm on top of? If not, is it more like the red color to the left, or is it more like the orange-yellow color to the right? So in this case, it's a bright red, so it's much more like this red over here. And I assign the label to it. So as I get more and more examples in to run through this tree, these decisions are made in such a way that I end up getting a label assigned to each one, depending upon the decision tree logic that was learned during training. So what does the algorithm look like? The card algorithm itself is fairly simple. Some of the concepts take a little bit of time to digest. So the card algorithm can use either entropy or the Gini impurity as a measure. We typically use the Gini impurity for most of our decisions here, just because. So in this case, our cart algorithm over here is taking the proportion of samples that are in the left subset, dividing it by the total number of samples. So we're basically weighting, W-E-I-G-H-T-I-N-G, each of these Gini impurities to determine which decision is the best decision to make. And I multiply that times the Gini impurity of the left-hand decision. Then I add that to the number of right-hand samples in the subset divided by the total number of samples, and I multiply that times the Gini impurity from the right-hand side. So this computes the purity of each one of the classes, and then whichever one is the predominant class is the one that I'm going to assign the label to. So in this case, there are two metrics used in making this split decision. One is the purity of the classes produced by the split, and that's measured by our Gini impurities over here, and then the size of each class. And this just goes back to simple statistics of if I've got more examples that represent this class than I have examples that represent this other class, I want to be able to weight that in such a way that it determines likelihood correctly. So a larger, less pure class may win over a much smaller, completely pure class. So that's one challenge with cart trees. And as I said earlier, this is also a greedy algorithm. So it seeks the largest information gain at each split, which means it may make less than optimal decisions at each level. But it does so in the spirit of trying to reduce computation time and cost. So this is the cart algorithm and simple decision tree logic. We're going to talk next on random forests and other ensemble methods and see how they improve over simple decision trees.